Hi everyone, welcome to my talk. My name is Tomohiro, and I'm going to give a talk about our paper, The Complexity of Gerrymandering over Graphs, Path and Trees. This is joint work with Matthias Bentert and Rolf Niedermeier from Technical University of Berlin. Gerrymandering refers to a practice of manipulating boundaries of electoral districts such that you gain political advantage. And this term was coined after an American politician named Elbridge Gerry, who signed a bill that resulted in political districts that looked kind of like a salamander. Modeling gerrymandering in real life, Cohen-Zimmer and Ido et al. Introduced a problem called gerrymandering over graphs recently. It is defined as follows. So first of all, we have an input graph which is undirected, and every vertex has some weight defined by W, and we have C set of colors, and we have a coloring function that assigns every vertex some color, and we have some special color P which we call target color, and finally we have K that specifies the number of districts. And the task is to partition B into exactly K districts, where when I say district, what I mean is a vertex subset that induces a connected subgraph, and we want to find a partition such that P wins the election. So I need to explain when P wins the election. So to do so, I would like to first explain when P wins a district. So we say that P wins some district B prime if for all other colors Q, it holds that the sum of weights of vertices of color P in B prime is strictly greater than that of color Q. And we say that a color Q wins district B prime, assuming that Q is not target color, if something similar holds, but instead of the strict inequality, we have non-strict inequality. And let MQ denote the number of districts that Q wins. Then we say that P wins election if for every color Q, which is not target color, the number of districts won by P is strictly greater than NQ. So let me show you some example. So suppose that K is equal to 2, and these numbers represent the weights of the vertices, and we assume that these orange vertices are target color P, and the black ones are the other color. Then, for instance, this partition into two districts is a yes instance, is a solution, because like in this district P wins, and if you look at this district, the weight of color P is equal to 5 and the other color has weight 4, so this district is also won by P, meaning that like both districts are won by P, meaning that P wins the election. On the other hand, if you look at some partition like this one, well, this is actually not a solution, because if you look at this district here, then the weight of P equals the weight of Q, meaning that Q wins the district here. So now we have that there's one district won by Q and there's one district 1 by P, which does not satisfy this inequality, meaning that this is not a solution. In fact, we can show that the one I showed earlier, this partition, is a unique solution for this instance. Let me start with what is known about paths and what we found about paths. Ito et al. Showed that when the number of colors is constant, then gerrymandering can be solved in polynomial time. That led him to ask, when the number of color is unbounded, whether this is polynomial time solvable or not. We answered this question in the negative, showing that gerrymandering over graphs is NP-hard on paths, even if every vertex has weight 1. And let me remark that Gupta et al. Also independently proved that gerrymandering over graphs is NP-hard on paths, but their reduction uses non-unit weights, so our hardness result is a slightly stronger. On the other hand, Gupta et al. Show that on paths, the gerrymandering over graphs can be solved in 2 to the 6, 19 to the k times polynomial time. Let me present how we showed that gerrymandering is NP-hard on path. What actually we show a slightly weaker statement. I would like to show that gerrymandering over graphs is NP-hard even if every connected component is a path. And to prove NP-hardness, we reduce from clique on regular graphs. Let's say that n is equal to number of vertices, m is the number of edges, and let's assume that every vertex has exactly d neighbors, and let large n be some large number. And we construct an instance like this. So first, let me go through the colors. So we use n plus 3 colors. So first one being the target color P, which is orange, and 2 colors Q and R, and we introduce vertex specific color CV. So it means that like for every vertex in H, we introduce one color CV. So for the graph, first we add n plus 1 isolated vertices of color P, and then large n minus n minus L vertices of color Q. And for every vertex in H, we introduce a path on 2n minus 1 vertices, where first n minus 1 vertices is Q of color Q, and the remaining vertices have color P, color CV, the vertex specific color. And then we also introduce for every edge in H a path on 4 vertices, where the endpoints have vertex specific color, and the inner vertices are of color R, which is only used in this gadget here. And we would like to set k such that we delete exactly this k bar many edges. And here k bar is equal to n minus L times large n plus dl plus L choose 2. Next, let me give you some idea about why our reduction is correct. So this is the construction that I presented in the previous slide. And I'm going to show the forward direction of the correctness. So suppose that H contains some clique K of size L. Then I would like to specify how this K bar many edges are cut in this graph we constructed. So if there's a vertex gadget whose corresponding vertex is contained in K, then we actually don't cut any edge from this gadget, meaning that like this is going to be one district. Whereas if there's a vertex whose corresponding vertex is not contained in K, then we would cut n edges, since there are n minus L of them. So we cut exactly n minus L times n, large N edges here. And if there's an edge, both of whose endpoints are contained in clique, then we cut all the edges. And if there's an edge gadget one of whose endpoint is contained in K, then let's say that the left one is corresponding to U and the right one is corresponding to V, then we cut exactly one of them. And by symmetry, if only V is contained in K, then we cut this edge here. And lastly, if there's a edge neither whose endpoint is contained in K, then we do not cut any edge. So if you look at the edges in the vertex gadget, we know that we cut exactly n minus L times large N edges, as I discussed earlier. So let me analyze how many edges we cut from the edge gadgets. So these 4 vertex paths. So if you look at edges that are not between the inner 2 vertices, well, we see that this edge is cut if and only if the corresponding vertex is in K, meaning that we are going to cut exactly D times L of them. And lastly, if you look at edges in the middle, well, because we only cut it whenever both endpoints are in K, we are only going to cut L choose 2 edges of such edges. And at this point, like, we need to analyze if like the way we cut edges actually results in the election where P wins. So let's do that. So first of all, P wins n plus 1 districts. This is because there are n plus 1 vertices that are isolated of color P. And moreover, Q wins n districts. This is because, like, if you look at this gadget here, this district is won by CB. Whereas, as I told you earlier, in this gadget we cut all the edges here. So here's one district that is won by Q, but since there are exactly n minus L of them, cancelling out the second term, we see that Q wins exactly large n districts. And if you look at R, well, we see that there are actually not so many vertices of color R. So this doesn't exceed n plus 1. And next, if you look at the colors, vertex specific color CB, where the corresponding vertex is contained in K, then we see that this only wins when in the edge gadgets. And this only happens at most key times. And finally, if you look at the vertex specific color whose corresponding vertex is not in clique, well, this actually wins n times in the vertex gadget here. But then because of the way we cut, in the edge gadget. So for instance, if you look at here, well, this district is won by the two center vertices R. So like this vertex specific color doesn't win, meaning that in this edge gadget, this CV never wins. So the only place CV wins is in the vertex gadget. And actually, it wins exactly n times. Overall, we see that the number of districts won by P, which is n plus 1, is greater than that of any other color, showing that P wins the election. And how we did it. So we would like to show that gerrymandering over graphs is weakly NP-hard even if the number of colors is equal to 3. We reduce from partition. So for input we have multi-set A of numbers, and we would like to find a subset of size n½ such that the summation of AI is equal to the half of the total sum, where the total sum is denoted by S. And we constructed the instances like this. So first of all, we use 3 colors. So one is the target color P, and 2 other colors, let's call them Q and R. And the graph is also not very complicated. So first of all, we have, let's call the center vertex Z, and we have exactly n½ leaves that are attached on this center vertex Z. And for every element AI, we attach basically 2 edges where exactly one endpoint is adjacent to Z. And finally, we set the number of districts to be 3n½ plus 1. And the trick comes in the weight. So let's say that like m and n are like really large number. Then we specify the weight of this xiq as m plus 2 to the I n plus ai, whereas we set the weight of yir as n plus 2 to the I n plus 2sn minus ai. Well, notice that there's a common term, n plus 2 to the I times n, and like one part is basically positive, as in like plus ai. The other term is kind of negative in that, well, this is kind of flipped, and instead of plus ai we have minus ai. And we also have for the other 2 vertices, namely xir and yiq, we have the term minus 2 to the I times n, to ensure that like these 2 to the I times n can be cancelled out. And using this kind of trick, we were able to show that this reduction is correct, but due to lack of time, I'm not going to give any details on the proof. And with that, I would like to conclude the talk. So we show that gerrymandering over graphs is NP-hard even if the input graph is a path and every vertex has weight 1. And moreover, on trees, even if the number of colors is equal to 3, the problem is already weakly NP-hard. So if you look at the worst case analysis, then this gerrymandering over graphs turn out to be a very hard problem. But that doesn't exclude any heuristics algorithms, so like approximation algorithms and so on. So maybe that would be the next step for research. And with that, let me conclude my talk and thank you for your attention.